Afternoon, everyone. So today, obviously, I'm going to discuss multi-storey timber buildings in New Zealand, some examples of existing projects, some lessons that we've learnt, sometimes the hard way, and how we might avoid those lessons or risks moving forward. So it has a project management flavour to this presentation, not highly technical. But there's a bit of lead in as a sort of caveat, I guess, the types of buildings that we're talking about. So at the moment, we're seeing obviously a big push for low embodied carbon structures for reducing embodied CO2 emissions within our built environment within New Zealand. That's one of the strongest reasons I think that it's coming through that consultants that might be less familiar with timber design are being asked to step in to offer solutions that would be engineered timber or low embodied carbon. There's all sorts of other reasons as to why we might go for an engineered timber solution, which I won't go into, but I guess it's just important to say at this point that there is an expansion in this market that's pretty evident, especially from the number of attendees today even. So clients across, whether it's government agencies or private developers, they're going to want to see these low carbon or engineered timber options. And like anything that's new, it comes with certain risks or uncertainties that should be dealt with as best you possibly can through the design and construction phase of these buildings. So there is a push for timber, that's the key point. And of course, there's a range of timber elements. If I just skip through them, here is a few examples. It's not like steel and concrete where you get pretty similar material. There's a UB or a UC, or the concrete has different grades or different additives. There is really quite a range of products and systems that exist in engineered timber design for multi-storey buildings, whether it be your traditional stick-build light timber framing, whether you're using glue laminated timber or CLT or laminated veneer lumber. There's all sorts of different supply chains that are associated with those products. And the adequacy or the strength of that supply chain should really impact on how you design these buildings to mitigate some of the risks, how you procure the materials, how you tender it, and how you then construct these buildings. So today, I just want to highlight that I'm really talking about lessons learned across, I guess, a few key materials. I can't cover off some of the more unique systems, but really the materials that I'm talking about today is mass timber systems incorporating glulam or LVL as usually framing elements, and cross-laminated timber for walls, floors, etc. So the first thing is that designers that are new to designing in these systems, they'll need to understand that for glulam in New Zealand, we've got Timberlab, Techlam, and that I guess were the most advanced suppliers in that space. Cross-laminated timber, which can come from Xlam in Australia or Red Stag Wood Solutions in Rotorua. Laminated veneer lumber, which would be Nelson Pine Industries or Carterholt Harvey via Timberlab, or for smaller scale stuff through Newcombe as well. So those are some of the key suppliers that provide backup information and have their own supply chains that we need to be aware of. Now, to describe, I guess, taking those components, putting them into a system, I just wanted to show some examples of what I'm referring to with these risk mitigation strategies. So putting CLT together as walls, floors and roof. This is an example project, which was one that I did when I was at Kirk Roberts quite a few years ago. Where it had, here you can see LVL framing, CLT floors, CLT walls, etc. Throughout that project. Other mass timber systems that we could consider when talking about these risk mitigation strategies is glulam or LVL frames, where you've got a moment resisting frame system or a gravity system effectively that's made out of glulam or LVL. Here's some examples where it's a post-tension timber frame that was, my topic at Canterbury Uni as part of the research that I did there. That's one example of a connection, but ultimately it's, LVL or glulam elements that are in large format in that beam and column arrangement. There could be CLT or LVL solid walls. They might be held down with post-tensioning rods. They might be anchored with base connections or proprietary arrangements to take the overturning actions. That's all considered. Other supply chains that are quite important, prefabricated panelized light timber frame. You might talk to the likes of the old Concision, who have now rebranded, Clevercore up here in Auckland, and a few other suppliers that are looking to get into this market in more and more scale. But I guess what I'm not talking about today, because I think that there's unique risk mitigation strategies that come with these systems, are really bespoke elements. So what I've got on the screen is something that we developed one-off for a project where we used round timber for the floor system. This was a long time ago for the Tuhoi project in Taniatua. So that will require unique considerations when you're doing bespoke elements that are one-offs. Or if you're looking at complex glue laminated timber structures, again, there needs to be a different approach where you're working very closely with suppliers. Long span floors have their own unique challenges because they're often a mixture of systems, the concrete options. Volumetric modular systems, again, unique risk mitigation because they're very restricted in terms of who provides those systems, what the compliance pathway can be, and SIPS panels. There's some examples of some of those long span floor systems, like the Podia system on the left, which is coming out of Nelson from Gavin and Andy Van Hout, and the timber concrete composite system there shown on the right, which the reason why I put it here is that there are unique considerations about the concrete mix and shrinkage control that's required for those systems. Volumetric modular, an example shown there on the left, and SIPS panels. Again, SIPs are being used by especially formants. I think that image is taken from a formants job on the right. But it's a wee bit unique about how you might de-risk that project, and involves a lot more engagement around compliance pathway, etc., in my opinion. So what I've done is I've broken down what I consider to be the key risks that exist when you're doing multi-storey timber buildings in the New Zealand framework. The first broad category is limited supply chain. And it's important to acknowledge, as you would have picked up from those previous slides, is that there is a broad range of products and systems, and each of those systems and materials have their own limitations around supply chain. You've got to work closely with that to avoid putting your client in a position of heightened risk around supply. And so there's factors that come into that limited supply chain to consider for not necessarily structural designers, but maybe it's the project manager on that job or the client to factor in. Lack of competitive tendering is one, potential for increased costs due to that restricted supply chain. What happens if you don't agree further on in the design process? Could you be held over a barrel because there is few suppliers, i.e., have some less competitive arrangements further down the road? Could there be lead time issues, supply delays, and capacity constraints that might affect the build program? I guess one of the benefits with mass timber and prefabricated engineered timber systems is typically that you can speed up construction on site with the systems, the DFMA type approach that you apply to these projects. But if the supply chain is limited and you're delayed in delivery, all of those best endeavours can be jeopardised. Second broad category is compliance issues. Really, there isn't a good amount of information in comparison to, say, concrete and steel around the standards or design guides for delivering these solutions or designing these solutions. So you are dealing with an alternative solution compliance pathway under the building code. So that's a peer review process. It requires, that the two engineers agree on a way forward and in a framework that is less well defined, i.e. there isn't a standard to refer to directly for a lot of elements and timber design. For example, the new timber standard 1720 doesn't have CLT in there, but yet there is a lot of CLT happening. Now, there's also some challenges around timber treatment, B2 compliance and requirements there. Certainly passive fire is a hot topic. And there's a lot of changes on the wind around fire design, delamination risk, fire load considerations that could potentially lead to delays in receiving a BC, a building consent, or your CCC at the end of a project, or could even require that if there's a shifting of the goalposts from the local territorial authority, might require a significant amount of redesign that your client would need to pay for. So again, that uncertainty around compliance is a risk that needs to be actively addressed. Now, the other broad area that, to be honest, there's overlap with these categories. Think of it as interlapping circles. The lack of experience in the design and construction team that can interrelate with compliance issues, of course. There can be uneconomical design, so that you're not really extracting the full potential of some of the systems through that lack of experience. There could be the wrong outcome. For example, if designers are less experienced with mass timber, they might put forward solutions that are uneconomical, and a client may have had an objective to do something that is low carbon and sustainable, but might end up finding that they're forced for financial reasons to stick with traditional concrete and steel construction for multi-story. Quite a common occurrence. The other aspect is that, I guess, when you're designing these alternative material solutions, that it is very important that there is broad experience across the design team. It can take one aspect throughout the design and the construction or tendering phase to effectively derail a mass timber job. So an architect that's familiar with timber is important. QS, structure, acoustics, fire, passive fire. Contractor, I guess that the contractor needs to really engage, and having early supplier or ESI is very important throughout the design phase as well as the delivery and construction phase. So those are the broad categories. What I'd like to do is to go through some example projects that we've been involved in or are aware of, identify some of the issues that have occurred, i.e. some risks that have actually come to manifest themselves, and highlight some of the lessons that we've learned throughout those, and then summarise how best we think we should mitigate those risks in future. So it's really about saying, we've learned the hard way on some of these jobs. We all need to do our best to deliver these solutions for our clients and grow the pie of low carbon sustainable construction. We're just keen to be open and share what we've learned to avoid repetition of mistakes. So example one is Otago Polytechnic. Again, this was a design that I did when I was with Kirk Roberts. It involved two wings. There was a student accommodation, so dorm suites, entertainment areas, and some administration areas on the bottom floor. It was on some really poor ground, so it had reinforced concrete foundations on ground improvement. To get some of the open spans in the lower areas, there was a use of LVL framing and braces at certain locations. But the key thing back at the time when this was designed, quite a number of years ago now, I think we're looking back at 2016. That was one of the largest CLT, well, for a long time until Auckland City Mission, it was the largest CLT building in New Zealand. But at the time, it was also one of XLAM's first large commercial jobs after Believe Backpackers. So it was, pushing the envelope about commercial delivery of CLT within New Zealand. And as well as XLAM, there was Nelson Pine that was supplying the LVL for that job. That's just another image showing some of the structure in behind. That's isometric showing a mixture of the LVL framing and the CLT, and obviously hiding the floor plate there, just to give you an idea. Now, first issue, again, this is not a comprehensive list across this project. I've just picked a couple of key items, and I've categorized them into what I'd consider firstly limited supply chain issues. So first issue, delayed CLT delivery to a bit of an argument. I don't know the details, but there was some issue around variation claims, or there was potentially some supply constraints. I didn't know the full story on that, but either way, there was delay in CLT. So the key lesson that I'd take from that is that there was one or two later design changes that really were difficult to accommodate and adequately price for, and feed that pricing through for approval at the time. So I guess the lessons that we've learned from that is just making sure that there is better contingency in the cost and program to deal with those potential last-minute peer review items or coordination changes, etc., and that the program is built to adequately allow for addressing those. And there needs to be, I think, more supplier pricing updates as we go throughout projects to make sure that there isn't surprises. So a lot of manufacturers are already doing a very open book approach to address these issues, but certainly for the client at the time, having a delay right at the end of the project on this one because of delivery and some of the contractual matters, it left the client without another option, because they, at that time, XLAM was the only one providing CLT. And so they really had to work it out quickly to avoid additional issues. The second key issue was really around CNC machining. So my understanding was that the CNC machining time required on this job was relatively high. So what we developed in conversations with, I remember having chats with Sam Leslie in the Corey Lounge in Dunedin about connections and detailing and CNC and castellations was a key thing. But basically we came up with some ideas to try and minimize steel fixings and cost. But I guess that the lesson there is that sometimes, trying to make savings but complicating the CNC machining can lead to delays and challenges, especially when you're dealing with a relatively new a relatively new supply chain in terms of CNC machining at that time. So try not to reinvent the wheel. Obviously minimize CNC machining by using some of the more standardized connections that the Europeans use, and obviously in seismic regions where you can. One other issue for now, this is in a compliance category, is with half lap joints, just a basic thing that comes with all DLT floor plates really. What happened in this project was that the gap between the individual panels increased for whatever reason during construction. Basically on the upper floors of this building, there was quite a gap between these CLT panels that developed. And I wonder if that was more of an installation issue of those CLT panels. The contractor on this job was their first large-scale CLT development. So there were special tools and equipment that were required to make those joints tight. Not sure if that fully landed in the end. But one lesson, or I guess a few key lessons that we've learned, is that if you are dealing with contractors that are new to the game with mass timber, as invariably you will be in New Zealand as we increase the amount of projects that we do of this nature, we need to have design handover workshops to say, okay, these are the DFMA principles or the construction principles that we've factored into our design. Make sure that all of that knowledge and consideration is well transferred over to the construction crew, so that they don't go off and reinvent the wheel and do things as they would with concrete and steel, for example. Make sure that you're there and active for the first of every component before problems multiply, because these buildings can go together quickly, and if you're not there at the right time, you miss that opportunity to cost effectively address things. Make sure that if you're dealing with a contractor that is very new to mass timber, that they consider specialist subcontractors or installers for the mass timber elements to de-risk it for their first time round, and maybe have a more hands-on engineer to contract role from a timber expert, or heightened construction monitoring as you're going through the build. Lack of experience, again, there's some overlap between these, I guess, broad categories. So CNC machining, you could argue that that's potentially, a lack of experience on the designer's part as we went through. Everyone was inexperienced at that time with mass timber. CLT half-lap joints exceeding tolerance for the pacifier, again, that's potentially could be categorized as a lack of experience on the contractor's part to make those joints tight. Potentially. And then I guess another thing that I just learned the hard way on this project was that this was one of those last minute design changes that came through. A half-lap joint was quite long because of acoustic flanking issues. There was no floating floor in this design, so limited ability to mitigate acoustic flanking. That design change of making a half-lap joint instead of 80 mils, making it 150, added quite a lot of cost because CLT panels needed to be flipped in the factory due to limitations of cutting those half-lap joints. So just little things like that can make a big difference. So it's all about knowledge around the supply chain. So example 2 is superlot number 1 up here in Auckland in Mangere. This involved apartment blocks. It was a hybrid system. It was walk-up. It had prefabricated panelised light timber frame walls that were done by Stanley's Modular. And then Blue Lamb LVL post and beam framing by Timberlab, and then CLT by XLAM. So it was a mixed engineered timber system. Some of the key issues that occurred on that job and lessons that we've learned is, I guess, just the need with, a limited supply chain. You're dealing with a mixture of different capabilities across shop drawing detailing. So I guess the image that's shown on the screen is the way that it should be done. It's not the way that it was actually done on this project, where you have a general arrangement model where you're bringing those supply chains together to make sure that you've got consistent dimensional tolerances, consistent, considerations around sequencing, etc. And at the moment in New Zealand, if you're doing, say, pre-cut, pre-nail framing, they're working in a very different system. It's usually 2D drawings that you're looking at, or at best DWGs, rather than modelling it in 3 dimensions and working through the key coordination aspects. So ideally, someone needs to take ownership of general arrangement of prefabricated elements to make sure that everyone's singing from the same song sheet to avoid tolerance issues. The next one was that Stanley's unfortunately liquidated halfway through this project, and so we ended up trying to figure out what a fallback option might be for delivery of the remaining elements or finishing of this project. Luckily, we were pretty much complete on the structural system at the time that happened. But try to factor in, if you're dealing with a limited supply chain, what would be your fallback option if the worst were to happen? Where would you go? and how would you finish the project. It'll help your client to no end if the worst does happen. Other issues with superlot number 1 on the compliance side. This is more just detailing. It's really going into the weeds here, but hold down connections. It's amazing how many challenges we've had around hold down connections, simply because when you do SED design of these types of buildings, 3604 goes out the window, your jib handy-brack goes out the window, and you're dealing with overstrength design, hold down connections and forces that are very large, but yet you are expected to have timber framing that's right on the edge of a slab for weathering and normal detailing for these sorts of apartment developments. So you've got some very large forces that are right on the edge of your slab, and those hold down details have led to a lot of challenges. So I guess the lessons that we've learned there is, what happens if if things are out of tolerance? How do you deal with that interface? What happens if your cast-in items that deal with these big uplift forces are in the wrong place? What's your fallback option? How do you deal with those slab edge connections, and how do we again just allow for those worst case scenarios on site, or design more effectively so that they don't happen in the first place? Here's an example, just an image where on the left-hand side is the detail as expected. On the right-hand side is what the contractor did when they couldn't install the hold down connection because it wasn't first fabricated with the reinforcing cage. So they chopped them off to try and fit them in. And that was one of the issues. We had to remediate all sorts of hold downs because of that simple sequencing consideration. Now, what we've learned is that the prefabricated or DFMA style reinforcement is sometimes a much better option. You're doing everything else on the engineered timber side of things as a prefabricated system. Why not shop draw your reinforcement and incorporate those critical hold down elements within that coordination? Now, on this project, there's, again, lack of experience. We could talk about how the shop drawings needed to be done as a general arrangement to avoid tolerance issues. We could talk about, how we successfully deal with timber hold downs and procure those elements. Another key aspect is how we deal with diaphragm design. There's an easy way and a hard way. Basically, you can use straps on top of the CLT floor, which is quite common, or you can try and use top plates and beams and elements to provide ties. There's pros and cons, but basically we've learned that using tension straps on the top of the CLT floors are much simpler. Example 3, I'll try to speed up a wee bit, conscious of time. The GAP project down in Christchurch. So it's a 5-level high-end apartment building. It incorporates elements that are prefabricated panelised light timber frames from Concision at the time, LVL moment-resisting frames from Timberlab, CLT floors from XLAM, light timber frame roof, and some RC foundations. Main contractor on this job were, they'll have to forgive me, but I don't remember their actual company names. I just know them as Phil and Blue, Phil Tompkins and Blue. So they were fresh to mass timber at the time. So there were some great lessons that were learned there as well. Jumping into it, that's another image of the back of the structure with the staircase going up, which is I guess the money shot from an architectural perspective. Around limited supply chain issues, there was, one issue that often comes up, I think is worth highlighting, is that with the lead times that are required for LVL manufacturing or timber frames in general in New Zealand, often there'll be a lot of pressure put on the design and the peer review team to finish the design early so that they can start to procure material to make the frames, factoring in the lead time and the limited supply chain that we have there. So we've just learned to be very careful about that. We thought that the The member sizing was locked in for the design. We thought that the splice connections were where they were supposed to be. But in the end, final peer review type items meant that certain materials that were procured basically needed to be recycled and used elsewhere because they couldn't be used in this particular project. So with alternative solution design, I mean, obviously expecting the unexpected is essential. You do have to come to a resolution and agree and make sure that as designers, you're really pushing back on material procurement. Take a conservative position to make sure that you've got your building consent in hand and the design is completed before anyone goes to procure material. And then make sure that the other consultants, the project managers, etc., are factoring in those lead times early, and ideally engaging with the supply chain as early as the beginning of developed design is my recommendation. Another issue around the compliance, moment resisting frame detailing. So sometimes what will happen on these projects is that, again, you're dealing with new systems, new typologies. This was the first multi-story timber frame in a building of this type using these types of connections. So what we were trying to do was to come up with innovative ways to reduce construction on site. And so we basically, with that innovation came, I guess, an increased risk of design issues or change because of the peer review process that we needed to work through, the uncertainty as to whether we would all agree about that new innovative solution that was put forward, where there weren't existing projects to refer to in the market already. So the important thing that I think is to just make sure that we've allowed for some fallback options if certain elements of the design that are unique or new, that they don't land the way that you thought they would after you work it through with a peer review, and make sure that you engage early with your peer reviewer on the structural design of these elements is super crucial, and the more engagement, the better, even if it doesn't always cover off all the aspects that you would hope at the time. This is just some example of some of the connections that were in that moment resisting frame. It's complicated. It's got to address fire, it's got to address structural requirements, etc., seismic action. So there's a lot to think about. And in the end, the splice connections here ended up being a lot more labour intensive than what we're aiming for in the original design. But it's the risk that we run. So I guess you could say that another manifestation of risk was that same moment resisting frame detailing, but coming from a position of lack of experience. So the peer reviewer and ourselves, we didn't have a whole lot of experience with those types of frames, so it led to change. Sorry, I'm just having a drink of water. Interestingly, lack of experience for the main con was not a significant issue because there was heavy engagement with Fill and Blue and Innovate, and basically we were working through ahead of time issues. And the contractor took a very measured approach with being slow and steady at those early phases, getting us to inspect before he went too far, and then speed up once they've really got a handle on it, rather than blazing their own unique way and wishing and hoping that it would all land from a review point of view. Example 4 is Otago Polytechnic Trades Training Campus or Trades Training Centre. This was a commercial structure on top of a concrete and steel design. Lower level was concrete because it was partially retaining. This was under the Shovel Ready project, if you remember those in the COVID times, and that's how it was funded. So it was a fast track program to secure that funding. The upper floors were constructed though of LVL moment resisting frames and gravity frames, CLT floors, LVL tension compression braces. What we had in the design was this building is used to train engineers. So one key driver from the client was to express, low damage or resilient or clever technology around the connections that could be talked to and expressed in the actual building itself. So low damage design aspects were incorporated in the moment resisting frame connections and in the braces themselves. The main contractor was Naylor Love, and the LVL was Nelson Pine, CLT was by Red Stag Wood Solutions. So there's just an image when they were close to finishing up the framing. So limited supply chain issues. So this here there was LVL lead time challenges or delays, basically due to the separation of the steel bracketry supply and milling that led to some complications, where you can see in the image there that the LVL is coming to site without the steel bracketry in there. What I prefer from a design perspective is that if you can install certain components, steel components in the factory, and have those delivered to site with their significant benefits. So that's something that I'll drive for as much as I can. Dry fitting in the factory can help avoid tolerance issues where, welds don't match up with rebates. And another key thing that we learned the hard way on this one was that, again, the supply chain, the machines that they use in Nelson Pine, milling of the LVL columns is very slow, very expensive. So again, that could be categorized as a lack of knowledge issue, but inadequate factory moisture weather protection. So this is another key issue that's a very hot topic in timber design throughout the world, but I think we still have some lessons to learn in New Zealand. So there's potentially more that could be done to protect these elements in the factory, to limit their exposure to moisture during construction, especially given the length of time that this was planned to be exposed for. And, classic one for limited supply chain is really lead time issues around screw and dowels. So as designers, we're often asked to do a last minute substitution of a whole bunch of different spucks to rotherblast to spucks or whatever it might be, fixings and elements. So again, that can be addressed with early engagement with those contractors, make sure that that they've sorted out who's supplying those fixings and there's adequate lead time in the program. Compliance issues. This was an interesting one in the design where we had epoxy rod connections that are just absolutely rubbish and fire, where the epoxy turns to liquid. Be careful about post-fire stability and how that will be impacted. You can see on this detail here where early stages, the column dimension on the upper floor, what's indicated there as level 3, was smaller and coordinated as such. But having column continuity was really important for post-fire stability of the structure. So that led to the milling that was required that I talked about on the previous slide. So, post-fire stability, understanding the limitations of not only the material, the timber itself, but the elements that connect those timber pieces and how it's detailed for fire. Very important. Another issue from our perspective, we spent most of our construction monitoring budget talking about moisture. So elevated moisture content did occur during construction. You can see there on the left mold growth. You can see on the right us doing our own moisture content readings as part of the CM for the project. So key lessons there is just that moisture management plans are essential and they need to be done before the final tender price is agreed on these contracts. We need to talk about in that moisture management plan the moisture content reading procedures, how frequently they're doing it, what they're measuring and where, what happens when temporary coatings that are applied in the factory expire in terms of they're beyond their 90-day life. What do you do? Mold removal is a key one. It was interesting to dig into that and to see whether is it a health and safety risk if you enclose mold, even if the moisture content is low? That was an interesting topic to dig into. Rapid weather enclosure, vertical staging, so thinking about your construction sequence, combining your prefabricated mass timber system with a prefabricated external wall and roof system to enclose quickly is a key consideration. And how do you then verify that when, say for example, the worst has happened and the mass timber has been exposed to excessive moisture over time, the moisture content of the timber deep within those mass timber elements is elevated. How are you going to verify that it's dropped down below 18% before you encapsulate or apply your sealing coats to that element? So there must be a procedure around how you do that and make sure that you're not locking that moisture into the element. So lack of experience, you could argue that again, the amount of exposure to moisture could be, where potentially a contractor hasn't understood or hasn't, got the background experience with mass timber solutions to understand how it can cost a lot more and delay the project if you do have elevated moisture. And one other issue that went around in a circle for a few months was to shim or not to shim LVL frames. So there was I remember a discussion that went on around just the particular contractor was concerned about tolerances, putting mass timber elements together. So they wanted to shim the ends of almost every beam in that design. And in the end, we had to work through a process, but it delayed the approval of shop drawings, etc. So that was a key lesson there, is to just make sure that whoever is leading those aspects of the shop drawing process and the review of the structural design, that they really do have experience of what's common in these types of structures. From a compliance point of view, I guess, as well as a design point of view, around just having experience. J-shaped buildings with timber braces, very stiff elements, can lead to massive forces in design. So we've found that we're going to push a lot harder next time to throw in seismic isolation joints where we can, because of some of the very big loads that we were getting in the knees of these buildings and having to design to. And just acknowledging that timber diaphragms can only handle so much, you are quite constrained relative to, say, reinforced concrete diaphragms where you can throw a whole lot of reinforcing at it. And timber can only do so much. So, speeding along, how do we mitigate these risks? I want to just highlight some key points of what we've learned, combining all of those lessons that we've learned, plus some others, and then summarising how you might proactively address some limited supply chain issues. You've got to try to maximise competitive tension, of course. The project managers will tell you that. But at the same time, as designers, we need to pick our suppliers early so that we can de-risk pacifier compliance, we can pencil in a supply slot, we can work with the manufacturers to get the best, most cost-effective outcome for a particular project. So what we're seeing is most effective is that designers will do concept and preliminary design considering as many suppliers as they can, plus do a benchmark concrete and steel solution so that a client can be well informed about the pros and cons of each method, tender to multiple suppliers at that PD phase, and then they ideally pick their horse at that point and become part of the design team with certain deliverables. We've also found that tendering on P&G to the ECI contractors at preliminary design helps to make sure that we're extracting the benefits of DFMA or prefabricated construction. If you don't tender on P&G until the end of the design, you can get into a situation where somehow the P&G for a prefabricated timber solution is the same as business as usual concrete and steel, which we know shouldn't be true. PQS feedback on the P&G costs and checking of supplier pricing, etc., and then make sure that for the ECI engagement, if you do have an ECI contractor from developed and detailed design, that there's a bit of an off-ramp if the prices don't match up with the PQS expectations. So a potential retendering that is allowed for in the program to make sure that there isn't, I guess, a client being held over a barrel at the end of the design. Compliance issues. So on compliance, front load the design and engagement, really important. Talk to your local council about your fire strategy. Move forward some of your fees into preliminary design phase. Do a few more connections to get feedback from the contractors and the supply chain. Make sure that you review the BIM process that's required on these jobs. So look at the design and modelling gaps. Where does your shop drawing start? Where does my model begin? Look at how you can address those issues proactively around what the supplier does versus what the design team does. And that will vary depending on the supplier, I think. And then just finally, just one example that comes up on every timber job that I've been involved in is just who's taking responsibility for the final location of a hole and CNC machined elements, because every single project, it might seem like a simple thing, but it leads to issues. Mechanical services are LOD 300, but the shop drawings need to be done bang on. So who's going to take responsibility, and how is that going to be signed off, the final position of those elements? And then expand on the deliverables of each design phase and show the interrelated elements. So you've got your normal process that you would design to, the normal design guidelines that you would have from Engineering New Zealand, etc. You need to expand on that to actively de-risk these projects. To address lack of experience, some key points here are that you should do lots of engagement with the design team and ensure that you're engaging with a design team that have mass timber experience and strong knowledge of the New Zealand supply chain. For those that are learning, as there invariably will be, make sure that solutions are presented from previous projects to try and avoid reinventing the wheel, so that there isn't many tangents that can be taken. Design team needs to have that ESI support. And if you're dealing with a contractor that's new to mass timber, do you need specialist installers in the mix? And if you are going to do an ECI process through developed and detailed design, make sure that your contractor has homework through that. They don't want to be sitting there on their phone in the meetings. They need to be delivering a moisture management plan, QA plan, construction sequence plan, really thinking about the design and how it's being detailed and delivered on, and have those clear deliverables so everyone knows what to expect when they go to site. Design handover workshops, we talked about that, and specialist CM to support those contractors that are becoming familiar with mass timber. Finally, when you've talked about that with your design team, everyone understands the key risk mitigation strategies for the particular supply chain or system. You need to really program that in and all agree on that early on. So incorporate those risk mitigation strategies in that program. And it might look something like this as an example. I don't expect anyone to read this, but as you're going through each milestone, whether it be concept, prelim, design, develop design, detailed design, all the way through to construction being complete on site, there are certain key deliverables that not just structural discipline, they're coming from other parties as well. Like you can see a few examples here where we're suggesting that there is a passive fire schedule created by the end of preliminary design for confirming compliance with supplier products to enable testing if it's needed for missing passive fire details. There's locking down services strategies, beam penetrations. There's interfacing with the BIM protocol and the shop drawing detailing and how that's done. So step out a bit of a program. In more detail, you can see an example here where in blue is the PD tender that we're talking about, where you tender to the main cons and PNG. maybe talking to multiple suppliers to ensure that there's some competition there. Back end of the design phase, some key things where we're talking about allowing our client to have a bit of an off-ramp with final awarding of the contract if ECI isn't working out well, or there hasn't been good engagement of the cost and the moisture management plan, or those other key deliverables. There's an off-ramp. And then just one thing that I thought was important to mention as well is that as consultants, we are often limited to structure in terms of our responsibility. But when you're getting into those early concept solutions, you've really got to highlight the risks and opportunities to your client, in my opinion, to mitigate the risk on their behalf as best you possibly can. Many times we've done that with clients, and we've found that they're fed it into their risk appetite matrix or other KPIs, and they've decided that they need to go back to traditional steel and concrete construction. For me, that's not a bad thing if they're not ready. They need to be fully abreast of all of the risks and issues. Also see how we're going to mitigate those issues for them and address those risks. But full disclosure, make your decision, stick with it. So in conclusion, I think we've got a strong history in New Zealand. We've got some great engineers, some great supply chains, very clever people. And we can see that the applications of mass timber and engineered timber in general is growing. There are systems that are available that are cost effective, durable, low carbon, etc. But we need to understand the risks, work together collaboratively to address those risks, be upfront, honest, and make sure that as we do these structures, that we are delivering successful jobs that grow the pie and that allow us to achieve our low carbon aspirations for New Zealand in the future. That's me, guys.
Thank you very much, Michael. That was really great effort that you did, an extensive and thorough investigation that you made on lessons and risk mitigation of multi-story timber buildings in New Zealand. That will definitely assist and help all design engineers, manufacturers, contractors to be aware of these issues before they plan using mass timber or engineered timber in multi-story timber buildings. So thank you very much for your time and your effort. And I'll pass you on to my colleague, Daniel, to take care of the questions and answers. Thank you very much again.
Thank you, Namir. Thanks, Mike. That was excellent. I think a really great snapshot of the last 3 years of timber engineering in New Zealand and what's happening now and what to look out when designing these buildings. So yeah, thanks very much. So there's a good number of questions. We won't be able to go through all of them. I'm gonna summarize some, and I'm gonna start with a very quick one. One person is asking if you could remind us of the name of the contractor and quantity surveyor of the Otago Polytech.
Yes.
If you remember.
The contractor on Otago Polytechnic Student Village, the student village rather than the campus development, was Naylor Love. And again, on the Trades Training Centre was Naylor Love. I can't recall the QS, sorry, at the moment, but yeah.
Thank you, Mike. Now, this is one question which is coming up more than once. It's a bit of a long one, so let me read it out quickly. So first of all, great presentation. The question is, why is New Zealand not adopting more of European or North American detailing and perhaps more standardized details in New Zealand, essentially rather than reinventing the wheel? And the second part is New Zealand a big market to have larger supply chain or ability to adopt overseas material perhaps? And finally, what about using more harmonized standards again from Europe and North America? So there's 3 questions.
That's right.
If you can answer them, we cover probably a third of all the questions in the chat.
Yes. So I think the the reinvention of the wheel that seems to happen in New Zealand, it's not, there is good logic behind it. I think there's a few key things that mean that we need to design mass timber structures differently from, say, the Europeans, or say what you would in Australia with some of their mass timber buildings. First one is the seismic design criteria that we have in New Zealand. So we've learnt over the years that our diaphragm design aspects are particularly onerous in New Zealand in comparison to other international requirements after the Canterbury earthquakes. So the Pisa type loading that you have to achieve with 1.5 times your elastic forces are very, very high. And so those large diaphragm forces can lead to more lightweight European style connections being maxed out and not being applicable. So that was, I guess, where the logic was with that chat between myself and Sam Leslie on Otago Polytechnic Student Village all those years ago, was to try and use bearing or encapsulation or different details to deal with those heightened seismic demands that come into the mix. That can also lead, with the seismic requirements, can also lead to different solutions over top of timber floor plates. So often you might see lime mortar screeds or concrete screeds be applied to the top of timber floors overseas. That can double the seismic action and throw a whole bunch of cost into your superstructure elsewhere. So you'll see that, I think in New Zealand, that we, well, certainly us, we try and steer away from heavy acoustic solutions on top of floor plates. So that's some of the reason why I guess that we have differing details in New Zealand, and we don't always copy paste the Europeans. But as I've highlighted in the talk, start with the detailing that's been done overseas. And if you can get it to work, you should, because it's usually been considered over a number of decades. And I think New Zealanders being isolated, we have this number 8Y attitude, which is great, but sometimes it can lead to reinvention where it's not required. In terms of the European options and supply, or the let's just call it international supply of mass timber elements into New Zealand, I think there are projects now that are popping up using international supply. I guess copying some of what's happening over in Australia already to a large degree. And I think the key issues that we have to tackle in New Zealand is really around code compliance. One thing that we've faced many years ago was Auckland Council wasn't prepared to accept the use of untreated timber. They were firm B2 AS1 compliance, which means radiata pine with H1.2 boron treatment. And because the international suppliers typically are untreated, European spruce or that sort of thing, it does lead to some compliance challenges. I know that they are being addressed and tackled throughout different projects and different regions with different degrees of appetite for different TAs to consider those solutions. But again, it's early engagement, and it's making sure that you know, the local council doesn't do a 180 on you at 100% detailed design, and make you revert back to a B2 AS1 durability solution.
Yeah.
I think that was most of the questions. Did I miss anything, Daniel?
No, thanks. There was one more question about the supply chain in general, but I think you answered that as well. Now, quickly, because you do mention treatment, one person is asking about what standards do we have in terms of treatments when it comes to mass timber? Maybe if you can answer here. Yeah, sure. So I think there's reference made in B2 AS1 to basically structural timber requiring H1.2, and I think that's been expanded to reference CLT as well. So my understanding, I'm not 100% clear on the detail right now, but we're often following B2 AS1 for the treatment requirements for mass timber elements in New Zealand, and that obviously supersedes in some parts the old NZS 3602 from the top of my head. Daniel, you might know if there's anything additional to that. No, I think that's still a status quo. Typically, I think the current status quo, which is perhaps more written for smaller members and light timber framing, is applied to mass timber as well. But that is exactly my understanding. So thank you.
Okay.
Now, there's other two group of questions I would like to raise. So one is, and you have touched on it already, but maybe you want to quickly repeat that part. So the question is mostly about, we don't have any design standard in New Zealand dealing with CLT. So the first question would be, why don't we have one? And the second question is, how have you dealt, or how has it been dealt with? Like you mentioned, peer reviewer. So maybe if you can quickly reiterate that part, because I think it is quite important as being considered one of the major risks at the moment.
Yeah. And this is my take on the current situation. There might be other factors, of course, that I'm not aware of, but my take is that there isn't really a CLT standard for design as of yet in New Zealand, because that would have to come with a manufacturing standard associated with it as well. And at the moment, there isn't a manufacturing standard for CLT in New Zealand. I think that might be on the cards in future. The Canadian guys, I think, have PRG 320, which assists with manufacturing standards for CLT. But once there's more standardization in the manufacturing process for CLT, then I think it will lead to adoption of CLT standards as it has overseas, for design. But at the moment, when we're designing these elements, we are making heavy reference to the Canadian FP Innovation CLT Handbook as an alternative solution guide. And again, with our peer reviewer, lots of early engagement, as much as we can at preliminary design to tick off fundamental design aspects. And to be honest, it's not limited to structure. It's also needs to incorporate structural fire considerations as well. So yeah, that's typically the way that we deal with it as an alternative solution framework. I guess that it would be great to have a design standard, but at the same time, I wouldn't want a design standard that is going to change significantly as the supply chain evolves in New Zealand anyway.
Mm-hmm. Thank you, Mike. Now, another topic you have touched on, and there's a few questions, is about shop drawing coordination, the FMA. So to sum it up, the question is, once the design has been completed and coordinated, who do you think would be the best person to lead the coordination? So the shop drawing part of the project. Do you have any opinion on that, or any idea of how we can address that moving forward?
Yeah, look, I think there's no set answer. It depends on a project and what the capabilities of certain suppliers are. So in some examples, you might have that the full shop drawings are provided by one of the main suppliers, and they effectively model what is being supplied by another supplier. And that's quite a common case. And so that that everyone's singing off the same song sheet with a general arrangement model. I've seen also examples where potentially the supplier is not prepared to take on the full ownership of those elements, and for good reason, where there might be another consultant, either the design team step up and provide somehow some shop drawings, or there is a specialist consultant that does that general arrangement of the engineered timber elements and the steel bracketry to facilitate coordination, etc. So it will vary on project to project depending on who that supplier is. That's why it's so important to select your horse, pick your horse for the supply at the end of preliminary design, early developed design, is that you can flesh out all of these strategies within your BIM protocol for a project, so that there isn't any nasty surprises at the end where all of a sudden shop drawings from different suppliers don't actually match up, and who's driving geometry and that sort of thing.
Yeah, it's a good point. I think, someone needs to make sure that this is being coordinated later on. And as you mentioned, there's a few new consultants who specialize in that. Now, following up on that, in your opinion, once the shop drawing model and drawings have been completed, who would approve or review them? Is it a contractor approving after review of the architect? What is your take, or what's your experience on that?
Yeah, so certainly the architects will still be reviewing shop drawings. Structural engineer will certainly be reviewing shop drawings and signing off on those. Where it gets a little bit murky is around the penetrations that go into elements. So that's where we'll often see that an architect will do a penetration plan, and they'll provide that to the suppliers. That penetration plan will have incorporated allowances for pacifier clearances or seismic clearances, whatever it might be, and they'll be checking off that penetration in the shop, that penetration plan in the shop drawing review. We will often model the horizontal penetrations going through beams and walls and that sort of thing. So we'll be checking those penetrations, but the size of those penetrations is provided to us. And that's where it gets tricky, is that the size of those penetrations can be provided to us as sleeves from a mechanical services engineer, where there's sort of all care and no responsibility around the final position of that hole. Or you can have your ECI contractor have engaged with their subbies early on to verify the position of those horizontal holes to make sure that it's going to work, that your water is going to flow downhill, etc. So that's where my preferred method is that you have the subbies engaged with the ECI process, and those subcontractors for hydraulics, sprinkler pipe install, etc., they have reviewed the services design and then are confirming that they're happy with the placement in the final shop drawings before they're approved. That's my preferred. Very rarely happens because of the lead times required to lock in shop drawings and get things delivered. So I had one slide where I highlighted who's going to take responsibility for a hole. It's a simple question, but honestly, it's given me half of my grey hair just trying to figure out the answer to that across multiple jobs.
I share your thoughts here, and I think what all of us need to understand, that by spending a bit more time doing shop drawing process, we can actually cut time later on, but that's something we still need to learn a bit more. So thanks for sharing your opinion on that. Now, last two questions. This one should be quick, if I might. A question is in terms of when you do structural design, what software do you typically use, and would you use finite element for connections? So maybe just high level, what's your typical approach, or what have you seen in New Zealand being done at the moment?
Yeah, so I think in New Zealand, for analysis of these sorts of buildings, where we can, we do equivalent static method and more simplified approaches to designs where they are very simple, small scale structures, very regular, and they fit those provisions. But if not, then we're into ETABS analysis. What I would say on the analysis of timber buildings, you're using ETABS, it's a great tool, but it's also very easy to overcomplicate a model for timber structures. So I think that if you're planning on using a software, software is the easy part. It's more the structural idealizations that you should make to adequately represent how the timber will respond. Modeling, your CLT floor as a shell is not, in my opinion, the right way to go, because your flexibility comes from connections. So it's about being consistently crude with your analysis. That's the key, and you can do that with a range of different softwares.
And one other part of the question was, what about connections? Would you do a finite element analysis on a connection, or more like hand calcs?
Yeah, so generally we would use, we'd use the best practice of 1720 with the brittle failure modes, etc., and that involves a lot of hand calcs. We wouldn't often do finite elements of an individual connection, but we may have to get into some of that for the fire provisions under 1720.4 in the future, but probably a story for another day.
I agree, and I think that that's more moving into the thermal analysis rather than the force analysis. Yeah, I agree with you, but as we speak, there's some stuff happening in the background in terms of fire provision, so hopefully this will be addressed. I think it's only once people start using those standards to see the issues or headaches behind, and then they need to be addressed. So yeah, let's leave it for another time. Last question, and I left it for the last part because I let you decide how long you want to delve into that, but it's quite a simple one. Could you use 3604 or NZS 3604 on a high-rise timber building?
No, not in its current form. So I wrote a paper for CSOT back in 2012 where I sort of jumped up and down about some of the assumptions that are made in 3604 and how they can lead to non-resilience in certain situations, and those issues still persist. So I'm a big fan, though, of standardization of design approaches. So I think there's two steps that would need to happen. First is that 3604 would need to be rejigged in terms of how they deal with bracing, with diaphragms, ductility assumptions, etc., across a few key aspects. Then I think there's potential to apply it more universally to maybe 3 levels instead of just 2, for example. But without addressing some of those fundamental issues that exist within the document, yeah, that's my position on that one.
Yeah, thank you, Mike. It is a bit of an interesting question, comes up quite regularly. There was a separate webinar on that, and as I understand, 3604 is being revisited, but it's also my understanding that certain aspects in terms of bracing are not fully addressed yet. So probably another item to see how it evolves moving forward. I think we draw this webinar to a close. We have addressed most questions, so thanks for that, Mike. I guess you might be available for other questions, so just contact Mike directly if you have more questions, or Timber Design Center, Timber Design Society are also here to help with that. So thanks again, Mike, on behalf of the Timber Design Society and all people in the audience. And thanks also to Namir and Caitlin for organizing these webinars. And see you at the next time. Thank you very much and have a good afternoon.
Thanks.